Hi, we're going to finish chapter 6 today. Lesson 6, 5, and 6, 6. We have a bunch of theorems and corollaries to go through, and a lot of them are pretty much common sense things you would figure on your own, but we have them, they talk about them, so we have a way to reference them within a proof. All right, let's start it right in. Theorem 20. Now, the thing I don't understand about Theorem 20 is we talked about this at the beginning of the year, but it had a different name. It was called the triangle angle sum theorem. Now we're referencing the same thing again, but he kind of renamed it. It's called the angle sum theorem, and now there's a theorem number. So really there's three ways to reference this idea that the three angles of inside of a triangle equal 180 degrees. I typically call it theorem 20 because it's just easier to write that than to write out the triangle angle sum theorem or the angle sum theorem. But I think we all understand at this point that all three angles of a triangle equal 180 degrees. Okay, so I'm guessing, but I think the reason he brings it up again is so we can have some corollaries, which are added thoughts to this theorem. So we have corollary 1 to theorem 20. Now, I typically, wow, what just happened? I typically write it theorem 20, corollary 1. Let me see if I can get this to work. Here we go. So that's the way I typically write it for Canvas reasons, okay? It's the same thing. If it was on paper, it wouldn't matter. But for Canvas reasons, we need to write it all the same way. All right, so if two angles of one triangle are equal to two angles of the other triangle, then we can just kind of understand that the third angles are equal. Now, in every other textbook that I've taught out of, this is called the third angle theorem. Now, of course, we can't call it the third angle theorem, but for proof reasons, but the idea is we're finding the third angle. Since we know all the angles equal 180 degrees, if they have two angles that are the same, I mean, if we start out with 180 for each and we subtract 72 from each and we subtract 35 from each, we have to come up with the same answer for both. So the third angle has to be the same. So again, I think the reason he gave it a theorem number now is so we could reference this idea for the corollary. All right, so when you're trying to find that third angle, you can't just say subtraction. We have to reference theorem 20 corollary 1. Now there is a corollary 2 and 3. Again, you can't just say on your proof corollary 2, because if you look back, theorem 17 has a corollary 2, theorem 19 has a corollary 2. So we have to say, theorem 20 corollary 2, right? All right, now this is a very easy idea. We understand a triangle is 180 degrees. The acute angles of a right triangle are complementary. So of course it is, because if we subtract away the 90-degree angle, we're left with 90 degrees. And that's for two angles. And we know that 90 degrees means complementary. So of course, that's what it means. But again, the reason we have this, so now we have a way to reference it within a proof. Now we're getting to the point where we have lots of theorems, postulates, corollaries, definitions, and you really have to know what's on your theorem sheet. Otherwise, you're going to spend all your time on your test searching for the correct, theorem, postulate, corollary, instead of saying, oh, I know there's one, and finding it quickly, instead of going through and reading every single line on your theorem sheet. Which kids waste a lot of time doing that. All right, third one. Again, we're going to write it all out. Theorem 20, corollary 3. Each angle of an equilateral triangle is 60 degrees. Now we knew that, right? Because we know the definition of equilateral, but we have a way to reference that. now. Because technically, the definition of equilateral is just that all the angles are equal. Or actually, equilaterals, all the sides are the same. Yes, let's back that up. Each angle of an equilateral triangle is 60 degrees. So equilaterals, all the sides are the same, therefore all the angles are 60. All right, but we know that. All right, now this is a theorem I've talked about before, because before we had a problem. It was in chapter 5, where this right here is an exterior angle, and like angle 1 is a remote interior, and angle 2 is a remote interior. And hopefully you remember that we would say like angle 3 is greater than angle 1. Of course it is. And we would say angle 3 is greater than angle 2. And the way I explained it is because when you add these together, it actually equals the exterior angle. So now we're finally doing this theorem. Theorem 21, the exterior angle of a triangle, so angle 3, which I numbered it the same way, which is kind of funny, equal to the sum of its remote interiors. Okay, so you're adding the two remote interiors. Again, your chapter 5 and 6 tests are together, so you have to make sure you understand the difference between the two. This is from chapter 5. Let me grab my theorem sheet. Okay. Let's find it. It's here somewhere. And yeah, it's theorem 12. Theorem 12 is the exterior angle theorem. The exterior angle of a triangle is greater than either of the remote interiors. So they are different. They're talking about kind of a lot of the same things, but again, you have to know what's on your theorem sheet and you have to know how to apply it to the situation. Now, we are finally finishing with all the ways to prove triangles congruent. So to recap, we know side, side, side. We know side, side. We know angle. That doesn't erase. Angle, side, angle. And now we're learning the last two. And again, I typically don't use the theorem number. I just want it to be easy for you. So I just use the letters AAS. Okay, now AAS, as you guys can probably guess, stands for angle, angle, and then the side. So it's all about the placement. So when we had angle, side, angle, we had angle and the side and then the angle. And so I always tell kids, like, put a finger here, and you can see your side is directly in between. And that's how you can tell it's angle, side, angle. Now today, if you put a finger on this angle and you put a finger on this angle, you'll notice the side is no longer in between. It's like up around the corner. So you have the angle, and then you have the side. So when you're doing these and you're getting confused, I always find what I have two of, and I put my fingers on those. And I know it sounds silly, but it actually works. I have two of those, and where's the third thing? Is it in between them, or is it not in between them? Okay, so this is angle, angle, side. Now the last one is HL. Now HL is very interesting because it's kind of like I told you there was no SSA or ASS, because there's not. If I give you this, ASS or SSA, this doesn't work, okay? It just never does. And the reason it doesn't, and this one does, because I want you to look, technically, what do you have two of? You have two angles, or two sides. Put a finger here, put a finger here. Is the angle in between them? No. Where's the angle? The angle is around the corner. So this is technically side, side, angle, or angle, side, side, but there's a catch. What kind of angle is it? This is a right angle. So The word or the letters HL. Why do we use HL? Because H stands for hypotenuse. And the L stands for leg. And can you have a leg or hypotenuse without a right angle? And of course not. So we don't call it SSA or ASS. We call it HL. You can, in your head, you can think of it as right angle, side, side. But we know, and again, I don't use the theorem number. I want it to be easy. I don't want you to have to look it up. Just call it HL. Okay, the hypotenuse of one triangle is congruent to the hypotenuse of the other triangle, and they have corresponding congruent legs, and they, of course, have to be right triangles, then they are congruent. Now, there is a video, and it's like 1.5 minutes long. You don't, and it's here if you want to look it up. It's very quick, and it better than what I can do explains why ASS or SSA doesn't work. And the idea of it, and I'm not going to do it justice. If you had ASS, what can happen is we don't know this angle. So what happens is when we don't know that angle, this third side, this side here, doesn't have to be in that location. So what can happen is we can flip it in. That's not great. But I can flip it, and that's isosceles. And so this could go away, and it still has the correct lengths of sides. And obviously, those two triangles are not congruent to each other. So if that confuses you, watch the video. It's very, very short, and it does a great job of explaining it to you. All right, so again, don't use your theorem numbers when you do this. And I know, I have weird rules for all these. I just want it to be easy. If you're proving SSS, just write those 3 letters. If you're proving ASA, SAS, just use the letters. And I usually capitalize them. And of course, I regrade things. All right, so here are 8 pictures. I want you to pause me and see if you can figure them out, and then come back and I'll go over them. Okay, so hopefully you have all of these completed. Now we need 3 pieces of information. We have 5 choices. Whenever they share a side, we know that is reflexive. So again, I always, put a finger on the thing I have 2 of. I have 2 sides. Is the angle in between? No. So it's angle, angle, or I'm sorry, side, side, and then the angle, which we can't do that, right? But this is a right angle. So when it's a right angle, side, side, we know that we write HL. So that one I feel is the trickiest of all of them. Meanwhile, number 2 is the easiest of all of them. This side is reflexive, so we have 3 sides. So this is side, side, side. Now, number 3, there's only 2 pieces of information. I need a third, which would be vertical angles. So again, you have a finger here and here. Is the side in between? No. So it is the angle, and then the angle, and then the third side. All right, moving on. Number 4. Again, I have a reflexive side. Now, this one's tricky because if I look at this second triangle, I see a side, and in between's an angle. So this bottom one is SAS. But the top triangle is not quite the same. I have 2 sides, but the angle's not in between. So technically, I have ASS or SSA. So they're not the same. So you can't prove it. It's a trick. It's not possible. All right, so if I fold you, fix your paper. Number 5, let's reflexive. Now we have to make sure both triangles are the same. It's not a trick. So I have a side, and I have the angle in between. The bottom triangle, side, and the angle in between. All right, so side, and an angle in between. So it's SAS. Now, some kids, as soon as they see that right angle, they say HL. And sometimes that works, but sometimes it's not going to be HL. Sometimes it's like angle, side angle, or side angle, side. Sometimes it's just an angle. Let's check it. So I have a side here and a side here. The angle's not in between. So it's side, side angle, but it's a right angle. So it's another HL. It was HL. All right, vertical, plug it in. All right, I have an angle and an angle. The side's not in between, so it's angle, angle, side. And the last one, I have a reflexive side, but I only have two things. I need a third thing, and there's nothing else to put in it. So this one is not possible. Okay, so we're going to do two proofs together. And I wanted to do these flow. And flow proofs typically only work really, really well when you're proving triangles congruent. They don't really work for other ones because I really like flow proofs because with triangle congruency, because there's always the same setup, 3 steps down, you know when to stop when there's a equal. It doesn't really work that way for other kinds of proofs. All right, let's go. AD is perpendicular to BE. AB is equal to ED. C is the midpoint of BE. So find BE, the left side is equal to the right side. Now we're going to look at it and decide how we're going to prove it. And this is right angle side, side. So that is HL. Again, there's going to be 3 steps. Now, here's where some people get confused because they're like, HL, what's the 3rd step? Well, you have to prove the right angle as well. And they don't have to be in this order, as you guys know, whatever order you want to go in. And let's see. This right here is going to provide us with an angle. So I'm going to put that in step 3. AD is AD is perpendicular to BE. And this is given. And we know perpendicular lines form right angles. Hopefully you can find that quickly on your theorem sheet. ACB and ECD are right angles. Just find it. What theorem is it? Theorem 7. Now, nothing's equal yet, so I have to keep going. So, if it's a right angle, all right angles are equal. Now, we have to talk about this. Now, this is what we put corollary to definition of right angles. We proved the angle. Did we prove it's a right triangle? Or did we just do what we're used to doing? We got to think about what we're doing here. I proved that the 2 angles are equal. Now, within the proof, I showed that they are right angles, but did I prove that they're right triangles? How do I do that? All right, so that means we can't do what we've always done, okay? So we have to back up the train. Now, this is a little bit different. Now, if we know they're right angles, can we then say they form right triangles? Of course we can. So now we're going to have to say triangle ACD and triangle ECD are right triangles. All right, so again, it's important to know that they're right triangles, not that just that they're angles that are equal like we did before, like with side angle side. So we need a way to know that it's a right triangle. So this is going to be definition of right triangles. Hopefully that makes sense. Now, what did this next thing tell us? Is that a hypotenuse or a leg? And honestly, if it's in your proof, it doesn't really matter, but let's just talk about it. AB, oops, I'm on the eraser apparently. This is your hypotenuse. So I'm going to put it up here in step 1. Given. So to backtrack a little bit, I know it's weird that in this step, nothing shows as it's equal necessarily. And that is the case, and that's just a weird thing about HL. All right, back up and let's do the last given. C is the midpoint of BE. C is the midpoint of BE. Now we're not finished. This is just like before. So the left side, BC, is equal to the right side, CE, in definition of midpoint. All right, now we could bring it all together and write your congruency statement. The first triangle could be in any order. I'm just going to say ABC. Make sure this is a congruent symbol. A corresponds with D, B with E, and C with C. And below it, I say HL. One last step. I need to prove that CA is equal to CD. And then I use my 5 letters, CPCTE. So, you guys know flow proofs by now. It's just a matter of adapting a little bit to make it HL. And the last one. AB is equal to ED. And we have some parallel lines. All right, and it says, do not use angle A and E. Find another way to complete the proof. So I'm trying to give you a hint here. Now, if these lines are parallel, let's use this as the transversal. Anytime there's parallel lines right here, that's an indication that there's angles and like corresponding angles, alternate interior, something like that. And most of the time, it's alternate interior. So, and that's the case here. We have these two angles that are formed, and they are alternate interior. Now, we need 3 pieces of information. The third piece would be vertical angles. So we have to decide how we're going to prove it. So you have the angle, but the side's not in between. The side's around the corner. So this is angle, angle, side. All right, so if you want to pause and see if you can do it and then, see if your answer is correct, or I'll talk you through it. So as usual, 3 steps. Angle, angle, side. We all know that it doesn't really matter the order as long as you have the steps. I'm going to go ahead and put the side as the last step, and this is given, short and sweet. Now, with the parallel, this one is a little bit longer. AB is parallel to ED. Now, we're going to have to get our theorem sheet out. All right, this is given. Now, if the lines are parallel, which they are, it forms equal alternate interior angles. So we have to think, is this a theorem 17 thing or a theorem 19 thing? And theorem 17 is always a test if they're parallel. All right, so let's look at theorem 17. I have my sheet here. These are alternate interiors. So, it's 19. I said that wrong. It's theorem 19. This is why we look at our sheet. Theorem 19, corollary 1. parallel lines form equal alternate interior angles. I even said it was a test, and I already knew the lines were parallel. Okay, backtrack what I said. It's theorem 19, corollary 1. The lines are parallel, and they form alternate interior angles. Perfect. So angle B is equal to angle D, theorem 19, corollary 1. Finished. Now, I need to write my verticals. You got to use 3 letters. ACB is equal to DCE. All right, hopefully we know which theorem, not definition, theorem tells us about vertical. That is theorem 6. Now we're ready to write our congruency statement. First triangle doesn't matter. I'm just going to say ABC. My pen will work. AB. Oh my goodness. ABC. A corresponds with E. And I'm using my markings to help me. B with D, C with C. And this is AAS. And then lastly, what you're trying to prove, CPCTE. All right. We are finished. Guys, this is the last notes for the semester. Go ahead and smile and rejoice a little bit. All right, it's been a good semester. Now we just have to take our test, review a little bit for your final, and take your final. And message me if you have any questions. Thanks. Bye.